There have been numerous efforts to advance battery technology, with lithium-ion seeing impressive improvements over the years. But despite the progress, demand for higher performance has not yet been met.
The demand is unlimited for a better battery today. Their performance was really starting to stagnate. The chemistry was reaching its theoretical limits.
But there have been breakthroughs that could be the next step in battery technology. Lithium-ion batteries contain a cathode and an anode, and using silicon instead of graphite, the commonly used material in anodes today, could lead to batteries with 20 to 40% higher energy density.
Why silicon? Because it has 10 times the capacity for lithium compared to graphite.
EVs will go 50% farther and charge in 5 or 10 minutes. Will enable the electrification of aviation. Silicon batteries will enable the electrification of heavy transportation.
Instead of 300 miles driving range or 400 miles driving range, for the same size of battery pack, you can potentially go to 600 miles or 700 miles driving range.
There's a lot of interest in the technology, from the US Army to Porsche, Mercedes, and General Motors.
From a demand perspective, we are working with more than 90% of worldwide battery manufacturers by volume.
In the final quarter of 2022, startups raised nearly $500 million. The global market size for silicon anodes is expected to grow from $1.2 billion in 2021 to over $208 billion by the end of 2031.
So I think it's now ready for the industry to really take it to the next level in terms of scale up the production.
It really ups the game and the energy density and the capacity of that battery, not just by a couple of percentage, but by leaps and bounds.
Silicon batteries were first identified as potentially transformational more than 20 years ago. But of course, it took a long time for industry to figure out how to make the material work in a way that was really able to be adopted by the battery industry.
Replacing graphite with silicon in the anode of the battery enables better energy density.
It actually takes just 1 atom of silicon to store 4 atoms of lithium. And by contrast with graphite, with carbon materials, it takes 6 carbon atoms to store 1 lithium atom. So it's 24x atomically advantaged compared to carbon.
Silicon anode has 10 times higher energy density than graphite anode, but silicon presents the challenge as well.
The challenge is that silicon is so good at storing lithium that it expands about 3 to 4x when you charge the battery.
And that swelling, after a few charge and discharge cycles, causes it to crack. So the key is to figure out how to keep it from cracking.
Silicon is already used with graphite and anodes, but only in small quantities.
Silicon's been used as an additive in sort of small percentage for a long time. Actually, the very first Tesla Model S vehicle had sort of 5% silicon mixed into the graphite, and most companies today are still at that 5 to 10% range.
But recent breakthroughs have enabled anodes to be comprised of higher percentages of silicon.
Back in 2006, my lab tried to solve this problem of expansion cause breaking. We utilized nanotechnology. Yeah, that was the key invention at the time.
In addition to improved energy density, they benefit from faster charging as well.
It has something to do with its crystal structure, and once lithium coming in during first charging cycle, it becomes amorphous. That means lithium can come in 3-dimensionally so fast compared to graphite.
We've demonstrated that we can charge to 80% in under 6 minutes.
And if you think about the implications of that for not just electric vehicles, but all kinds of energy storage applications, it's truly a transformational technology.
Several companies are working on developing silicon anode batteries, each with a different method of managing its stability.
We use a carbon scaffold as the basis for our material, and then we incorporate nanosilicon into that scaffold to make a material that's about half silicon and about half carbon, the carbon providing the infrastructure, if you will, and the silicon really providing the performance advantages.
Group 14 Technologies, started in 2015, is commercializing advanced silicon battery materials.
Group 14 makes anode materials only, and so essentially we make powder and ship powder to our battery manufacturer customers, and they integrate that anode powder into their battery manufacturing processes. So today we're really focused on consumer electronics because they move the fastest, and as a result we are commercial now in smartphones through ATL.
The company has received investments from major battery industry players. It recently closed its Series C, led by Porsche, bringing total funding to $614 million.
the head of R&D for Porsche. He said at Porsche, the soul of the vehicle has been the engine and the transmission. They believe the next soul of the vehicle is going to be the battery cell.
Group 14 operates a pilot plant at its Woodinville, Washington headquarters. It's also nearing completion of a 10-gigawatt plant in South Korea, built in partnership with Korean battery company SK Materials. It's just starting construction of a 20-gigawatt factory in Moses Lake, Washington as well.
It will be the world's largest manufacturing facility for advanced silicon battery materials.
Sila, founded in 2011 by a group of ex-Tesla battery engineers, is working on silicon anode technology first developed at Georgia Tech. It spent the last decade developing materials called nanocomposite silicon.
We've had to iterate over 70,000 times to really dial in the recipes to make it work, but ultimately reached a breakthrough performance in 2021 and launched the product in the market.
The company has raised nearly $1 billion to date.
We've been in the market for over 18 months now. We shipped in a consumer device called the Whoop, which I'm wearing. It's a fitness and performance tracker. They're able to get 5-day battery life thanks to our technology. Our first automotive customer is going to be Mercedes. They announced a supply agreement with us to put us in their electric vehicles, and they're going to start that with the iconic G-Wagon.
It's been manufacturing at its Alameda, California headquarters since 2017, where it runs a 24/7 operation.
This here is our manufacturing facility at Sila. This facility here has been running for 3 to 4 years, and we're now producing material that's going to commercial customers and going to automotive customers for validation purposes.
To scale to automotive volume, the company is planning to build a 20-gigawatt plant in Moses Lake, Washington.
We have confidence that we can scale another 100x up to the factory scale at Moses Lake.
Amprius Technologies, started in 2008 in Fremont, California, was born out of technology developed at Stanford University.
We designed our first silicon anode structure 2014. We built the first manufacturing equipment in 2016. We received the first commercial order from Airbus 2018.
The company has raised around $170 million to date, and in 2022 it went public through a SPAC. It says it's developed a pure silicon anode.
We've brought to market a critical solution that is perhaps the holy grail of solutions with 100% silicon.
Amprius developed technology to stabilize the silicon, so it's less prone to swelling.
This is our Centrotherm tool. It's used to grow the actual anode material. So the nanowires will nucleate in certain spots on the metal foil, and then they'll grow upward. The reason those nanowires are so important is they create much more surface area than a typical battery.
Since 2018, the company's been in limited commercial production, with customers such as the US Army, Airbus, AeroVironment, and BAE Systems. As it works to scale up manufacturing, it's focusing on the aviation industry first.
It allows us to showcase our performance. They're also less price sensitive since they're high performance applications, and we're able to therefore get into the market very quickly with an advanced application.
We select aviation because we have a limited capacity today. Now, once we scale up, we can get into other market applications such as the electrical vehicle.
At its Fremont facility, it's built a pilot plant capable of producing a few hundred kilowatt hours per year, with plans to expand that.
We're expanding locally our pilot production so that by around this time next year, we should have 10 times that capacity.
Amprius recently announced plans for a gigawatt-hour scale factory in Brighton, Colorado, that it aims to open in 2025. All three companies received grants from the U.S. Department of Energy, totaling $250 million, as part of President Biden's infrastructure bill. Silicon anode manufacturing is just starting to ramp up, but getting there will be a challenge.
When you're going from lab scale or pilot scale, which is where we are today, pilot scale, to mass production, that's a very heavy lift.
I think the time to build and build the right team, probably the most challenging part for us.
There's a lot of work to do in America to get us to lead in the next generation of energy technologies. We haven't produced batteries, we haven't produced battery materials here in the US historically, so we're learning how to do that. But that's a challenge worth undertaking.
The costs are expected to be reasonable, improving over time. This could have big impacts for devices heavily dependent on large battery packs, such as EVs.
The battery pack is the dominant cost of an electric vehicle today. The key is to get it to below $100 per kilowatt hour. And already there's movement that is showing that it's doable, and some are doing it.
You can use smaller battery pack to get to the same 300 miles if you do silicon batteries. That will help reducing the cost for the long term, and it will be lighter weight, so it can have multiple benefits depending on how you use it.
For all cars to go electric, we need enough of this product for about 100 million electric cars every year. And the scale of that is going to be several $100 billion of anode material required.
If every car made last year had been an electric vehicle, that would translate to $1 trillion battery market. Now the question isn't whether we're going to reach $1 trillion battery market size. The only question is when.
And graphite is in short supply, so switching to silicon could help ease supply constraints.
Silicon is the second most abundant material on the planet, so there's no sort of scarcity issue.
There's also environmental benefits to switching from graphite, which is mined out of the earth and then refined. We're able to actually derive and synthesize our material in much cleaner ways.
China produces the world's largest supply of silicon, with an estimated 4.5 million metric tons in 2019. Behind them is Russia, which produces 600,000. The US only produced about half of that, at 320,000.
This can be easily ramped up. There's no geopolitical, sensitivity using silicon.
While the technology is young, there's a lot of competition in the space.
There are dozens of companies trying to solve silicon battery problems because the opportunity is so immense. And we encourage those companies. You know, this is going to be a global industry, and we can't do it all by ourselves.
We believe in silicon, and we're glad to see many other companies enter the silicon space, if you will, because that validates it, and it demystifies whether or not it's a scalable technology with a real solution in the market.
We've only really had a handful of commercially viable rechargeable battery chemistries in the history of mankind. The graphite anode that was invented and won the Nobel Prize and launched in 1991 is the same anode that powers your phone, powers these cameras, and powers your electric car. And this technology is really the first that can replace that entirely and is commercially ready to go.